Hello, I'm Hugh Manfield and welcome back to my science channel. Now today I'm going to be talking about what Einstein got wrong. And if you like my videos, please go to Amazon.com and support me by picking up a copy of my book, Einstein and Aliens. Well, in 1911, Albert Einstein published a famous paper, one that launched him to international fame. And within this paper, he predicted the deflection of starlight would be twice as much as predicted by Newton. And in 1919, an expedition off the coast of Brazil confirmed Einstein's prediction, and it launched him to international fame as the man who overthrew Isaac Newton. So I'm going to go through some of the development that Einstein did in his paper and some of his reasoning, and I'm going to explain where he made a colossal mistake. In his paper, Einstein set out with an accelerated system. Here I've drawn a rocket moving through flat space, far from any large massive object. So it's basically in a Galilean reference frame, and he called that reference frame K. Einstein then imagined a homogeneous gravitational field where the acceleration is the same wherever you are in all directions. And I'd like to point out that such a field doesn't exist in nature. It only exists in Einstein's imagination. Real gravity fields vary in direction, with the line of action always pointing to the center of the mass, and they vary in strength, being strongest down low near the surface of the object, and they reduce as you increase your distance away from the object, and eventually at a certain distance they become essentially zero. But Einstein set out to show the equivalence between these two systems. Einstein showed in his derivation, he imagined a clock up high within the system and a clock down low. And I've put all these clocks on rockets. This rocket is out in space, thrusting at a constant acceleration. This one's in a gravity field of Einstein's imagination, and this one is in a gravity field that we find around a massive body. Now, Einstein said that in each of these fields, if we emit a photon from this clock and it travels downward relative to the gravity field or the acceleration field, it will arrive at the clock below with greater energy, indicating that this clock is at a higher gravitational potential. Objects will fall and they will have higher energy when they reach the clock below. And he said the same thing will be true of this clock, and the same thing will be true of this clock. Now, so far so good. But then he said that due to relativity, a clock lower down in a gravitational field will run more slowly, and a clock higher up will run more quickly. And then he made the claim that if this is true for the field that he used in his example, which was his imaginary homogeneous gravity field, then it would be true for all fields, which is a pretty big claim, and he didn't have any supporting evidence or math to back up that claim. He simply asserted it. Well, let's assume that Einstein was right about this. So we have our rocket accelerating in free space at a constant rate, and in this case we've added another clock. I've lengthened the rocket, so this clock should be running faster than this clock, and this clock should be running faster than this clock. And it should be happening by the same amount. The amount that this clock runs faster than this one is the same amount that this clock runs faster than this one. And by Einstein's assertion, the same thing is true in the gravity field. So we can do this again. I've added a fourth clock. Once again, this clock running faster than this one, running faster than that one, running faster than that one. So however much this clock is running faster than this clock, multiply that by 3, and that's how much faster this clock is running faster than the base clock. Now, we could continue this on and on forever, and you might be starting to get an idea that something's a little bit fishy here, because we could end up with a clock an infinite distance above that is running at an infinite rate, which is a nonsensical result. So Einstein might have a problem, but he could probably wiggle his way out of this one. So let's look into this a little bit further. We have our rocket accelerating at a constant rate in flat space, with the clock in the nose running faster than the clock in the tail. And we put an identical rocket side by side with it. So this clock should be running at the same rate as that one, and this one should be running at the same rate as that one, and they should both be faster by the same amount. Now for our second rocket, let's connect it with a very, very long tether to a massive object at a great distance away, so that it's going to fly along the curve of a very great circle. We'll start our experiment with the rockets at rest with respect to themselves and the mass, and we'll pull the slack out of the tether. Then at the same instant, we ignite both motors and both rockets begin to accelerate, one along a straight line and one along a very great arc. Now in the first few moments of the experiment, we don't have to deal with any side load on the tether, because it's going to take a while before it builds up enough velocity to create a centrifugal force on the rocket. So during that early time phase, these clocks should still be behaving just as they were before, when both rockets were flying in a straight line. So now let's begin adding more clocks higher up in the rocket. So this clock's running faster than that one, this clock's running faster than that one, and these clocks are doing the same thing. The only thing is, on this rocket, if we drop an object, it's going to fall along the circular arc, which is the acceleration vector, rather than a straight line. But if an astronaut was on board this rocket, he would have to climb a ladder to get from one clock to the other. If an object was dropped, it would drop essentially along the axis of the rocket, just as it would here. And there's no real argument that these clocks should behave any differently from each other. So we have this clock running faster than this one, and this one running faster than this one. So we can add more and more clocks. And in this case, we add them in a straight line. And in the case of this rocket, we add them on the large arc. So we get faster clock, faster clock, faster clock. And we keep adding them around and around and around the circle until eventually we're getting faster and faster, and we come around the bottom of the circle, adding more clocks, and finally we come up and we add our clock here, and Einstein, we have a problem. Your fastest clock, which is running way faster than the original clock, is below the original slowest clock. Something is not right. So if we take a look at a rotating disk, and I'm not talking about constant rotation, I'm talking about accelerated rotation, an increasing rotation rate, as if we had rockets attached to the edge of the disk. And we place clocks around that disk, and I've shown 8 here. We probably have more like 800 or 8,000 on the large disk, so that there's only a fraction of a degree between each clock. So along the rim, as the disk is being accelerated, if you were riding on that disk, you would have to climb to move in the clockwise direction, and moving in the counterclockwise direction would be like falling or going downhill. A photon arriving from one of these clocks from the clock above would have greater energy, indicating that the clock above has a higher gravitational potential. But if we place an observer at the center of the disk, all of the clocks are at the same radius, all of the clocks are sharing the same motion, all of the clocks must be running at the same rate. So Einstein's assertion that the gravitational potential determines the rate a clock runs in a gravity field is clearly wrong. Now, it may take some time for this to sink in. Einstein was wrong. The whole basis of his 1916 theory of relativity was that a gravitational potential affects the rate that a clock runs. Well, here's a case that it doesn't. Here's a case where all of the clocks run at the same rate, yet each clock is at a higher gravitational potential than the one below it. So this kind of takes the general out of Einstein's general theory of relativity, and it puts the lie to his assertion that a higher gravitational potential changes the rate of a clock in all fields. So if his 1916 theory doesn't apply to all fields, maybe it only applies to a few fields. It's really not a general theory. And in that case, what good is it? Well, you might say, well, this is just a special case. And really, we don't need to examine this case because it's very unlikely to happen. Well, actually, that's not true. And it gets worse for Einstein. If we take a look at our rocket on a tether, flying in a curve, and an identical rocket parallel with it, flying in a straight line, if we increase the length of the tether to infinity, the radius of the arc becomes infinite and the arc becomes a straight line. A rocket accelerating in a straight line is of the same case as a rocket flying around a circle. And if the clocks on the rocket flying around the circle are all running at the same rate, then the clocks on the rocket accelerating in a straight line must also be running at the same rate. And this is very damning to Einstein's 1916 theory. So here's what Einstein missed. Basically, there are three ways to experience gravity, and only three ways. And really, when you think of it that way, there's really no need to generalize a theory of relativity. We can understand everything we need to know about linear acceleration from Newton's laws, and we can understand everything we need to know about the accelerations and the gravity that you would feel in circular motion based on Newton's laws. And with a massive body, we do have Newton's laws of gravity, which will give us the acceleration field. But wait a minute. Einstein predicted a greater deflection of starlight, and it was observed. So clearly Newton's laws aren't good enough to cover massive body gravity. So these three forms of gravity are all you need to describe any type of motion. For example, suppose we have a roller coaster on the surface of a planet, like we do have all over the Earth. Do you think roller coaster designers use Einstein's theory of relativity to calculate and design their roller coasters? No, they break it down into these three forms where you would have circular motion when the roller coaster is going around a curve. You have acceleration when it's braking or being pushed or just due to friction. And it's all operating in the gravity field of the planet that it's on, which in this case is the Earth. Einstein's attempt to generalize gravity was really misguided and unnecessary. Now let's go back to his 1911 paper. A homogeneous gravitational field is something that exists only in Einstein's imagination. We can picture a rocket accelerating at constant rate through space, and we can calculate all the effects that an astronaut on board would feel based on Newton's laws. And if that astronaut dropped an object, that object would enter into an inertial reference frame, and we would see that the rocket accelerating upward relative to that resting frame, where the object is now obeying Newton's first law instead of Newton's second law. The rocket would accelerate relative to that object, and that object would appear to fall and accelerate downward to someone on board that rocket. Now, in Einstein's mind, he was convinced that gravity is a different process from acceleration, and therefore he needed to imagine a homogeneous gravity field, and within that gravity field then he had to create an imaginary law that gravitational mass is equal to inertial mass. So this is typical of Einstein, to create all this complexity around an issue when he could simply have said gravity is acceleration. And that's really what it is. There's no need to consider an imaginary field. There's no need to consider an imaginary gravitational mass. There's no need to consider a new law of physics that says the gravitational mass is equal to inertial mass. It's all only something created in Einstein's mind. None of this occurs in the natural world. What we find in the natural world, linear acceleration, Newton's laws, and that's all we need to understand this situation. So Einstein was wrong about the conditions that are required to cause a clock to run at a different rate. It's not the gravitational potential, which I've clearly shown in this case, and which is also true in this case, and would also be true even in Einstein's imaginary case. None of these obey his law of gravitational potential changing the rate of a clock. All of these will run at the same rate. His theory of general relativity is fundamentally flawed. So what was going on, and how did Einstein get the right answer? Well, in each of these cases, we can tell what's going on by applying Newton's laws, and then if we know the velocities, we can apply special relativity, and we can understand everything that's going on there. Over a massive body, what you'll have is an increasing strength of gravity field and a decreasing strength as you go up, and you'll have a change in direction as you move around that body. So what's happening is something around a massive body that's related to the potential, but is not the potential, but is closely related enough to the potential that Einstein was able to get the correct answer. So by luck, he used the formula for gravitational time dilation at the surface of the sun and the surface of the earth. That's essentially what it boils down to, even though he disguised it as using the potential in his paper, and he was able to come up with the right answer. Well, actually, in his paper, he predicted half the effect and had to double that to get the correct amount, which he later published in a correction. So it's not the potential in a gravitational field that governs the rate of the clock. But Einstein used potential, and he luckily got the correct answer. So Einstein got the right answer for the wrong reason. Now, where have I heard that before? The implications of this may take a while to sink in. It will take someone who's educated enough on Einstein's theory of relativity to understand how I've just cut the legs out from under it. His pedestal is crumbling, and the world needs to wake up to the new model of fluid space theory. We're never going to make it to the stars if we have to keep hobbling ourselves using Einstein's flawed thinking. Einstein's theory of 1916 has no foundation. So until next time, I'm Hugh Manfield.